So, we were talking about redox reactions, and we talked about things gaining electrons, and I told you that when things gain electrons, their charge decreases or oxidation state decreases. And I talked about oxidation, which is the loss of electrons, and the oxidation state increases. So, whenever you see charge of something increasing, that's a loss of electrons. And we talked about how to calculate oxidation states. This is something that you have already done in O levels. And we also talked about balancing redox reactions, that the number of electrons gained and lost, they should be equal. So what we are going to do is we're going to practice more questions where we want to make the number of electrons gained and lost equal. Just for that, just 1 second, let me copy a few questions. 1 second, where's the... So I'll just copy a few more equations. So now there's an equation where... Which equation did we do last time? Last time we did the Cr2O7 equation. Now what I'm going to do a different equation. We're going to try and balance it. So the equation is 2IO3 minus, it's IO3 minus 1. And it's reacting with N2O plus H plus 1. And the products that are being produced are I2 plus NO and H2O. So 1 second, here's the reaction that's in front of you, and I need to balance this equation. So the number of electrons, the first thing is I need to figure out who's getting oxidized, who's getting reduced. So can anyone tell me what the oxidation state of I over here is in the first one?
+5.
Okay, so this one is going to be, it's going to be +5, and oxygen is -2 over here. So how did you figure this out? It's going to be I is X, that's the unknown. Oxygen is -2, and there are three of them, so that's -2 times 3. And the total charge on the entire thing is -1. So if you solve for this, X comes out to be +5. I said, what about N2O? What's the oxidation state of N and O over here?
N plus 1, O minus 2.
Okay, so N is exactly. So N is X. There are two of them. Oxygen is -2. The total charge should be equal to 0. Solve for this. X comes out to be +1. And O would be -2. H is already +1. I2, that's a neutral element, that's 0. O is -2. N is by default +2. And then H is +1 and O is -2. Okay, so I have all the oxidation states now with me. So which one is getting reduced? Like who's gain?
Iodine.
So iodine goes from +5 to 0. So that's a reduction in charge. That is reduction. And exactly how many electrons it gains? It gains 5 electrons. So remember, if the charge is decreasing, that means electrons are being gained. So iodine goes from +5 to 0. And who's losing electrons?
Nitrogen.
Okay, so nitrogen goes from +1 and it goes to +2. So that means it lost exactly 1 electron. So it lost 1 electron, and I need to make the number of electrons gained and lost equal. So what do I multiply both with? Uh, what do I have to do?
I think nitrogen by 5 only.
See, I'm going to multiply this by 5. I'm going to multiply this by 1. Right? Then the number of electrons gained and lost. So that means That means there should be 5 nitrogens. Now the problem is that I would have to go into fractions to make this 5 nitrogen. So think of another number so that they're equal. We can double that because it would be very hard to make this 5 nitrogens because I would have to multiply it by 2.5, and iodine should be 1. So I need to make this 1 iodine, so it has to be half I2. So without going into fractions, I'm going to double this. What I'm going to do is, so that I don't go into fractions, uh, I'm going to think of a number that's higher than that. Multiply this by 10, so that's 10 electrons lost. Multiply this by 2, so that
Sir, can't we use fractions?
you can use fractions, but I mean, it's better to avoid fractions. I mean, you can use fractions, that's fine. I'm just trying to avoid fractions so that we have nice whole numbers. So, so lost electrons, that's 10. Gain electrons, so there should be 2 iodines. There's 2 iodine over here already, and there should be 2 iodines over here as well. And on the other side, there should be 10 electrons that are 10 iodines, sorry, 10 nitrogens. So I would multiply this by 5, and I'm going to multiply this by 10 to make it 10 nitrogens on both sides. And now this part is balanced. Okay, this is balanced, this is balanced, the iodine is balanced, and you can now go on to balance the oxygens. There are 5 oxygens over here, so there should be 5 water molecules, not 5 water molecules. We don't have 5 oxygens, we have 11 oxygens, so that's 6 over here, and the 5 over here, so that's 11. There are 10 oxygens already over here, that's the 11th one, so that's already balanced. There are 2 hydrogens, so there should be 2 H plus 1 ions on this side. That's it. So now this equation is balanced. TK, is this clear?
Yes, sir.
So let me just copy one more equation. So so here's another reaction where you have uh, P4, and it's reacting with NO2 minus 1, and there's OH minus 1 and H2O. And in the products you have H2PO2 minus 1, and you also have N2O. So so here's my equation. So let's try and balance this one. The reason we're practicing this is because the entire electrochemistry you'd be doing this. So let's try and balance this one. What's the oxidation state of P over here? Sorry, this is
Sir, I can't view this.
now you can. So what's the oxidation state of P?
0.
Okay, that's 0. What's O is minus 2, obviously. What is N? I mean, there are 2 oxygens, so that's minus 2 times 2. And the total charge on the entire thing is minus 1. So what would be N?
Plus 5.
It's not plus
Plus
5.
3.
Sir, plus 3, yeah.
It's plus 3. So anyways, O is minus 2, H is plus 1, so this is also plus 1, and O is minus 2. What about P over here in this one? Plus 1 into 2, that's H. P is not known, then you've got minus 2 times 2, and the total charge is going to be equal to minus 1. So what is the value of X?
1.
Is it plus 1?
Yes.
So this is plus 1, O is minus 2, and H is plus 1. So anyways, N2 again, that's N would be plus 1, would come out to be plus 1. So those are the oxidation states of all the elements. ठीक है? Minal, is this clear? Adam, is this clear?
Yes, sir.
So now the next part is that you have to figure out who's losing electrons, who's gaining electrons. So what happens to P? Losing or gaining?
Losing.
ठीक है, so it gets oxidized, loses how many electrons? One electron. One. अच्छा, when I write one electron, that's loses one electron. That is for one P. ठीक है, I'm just talking about a single P atom, not the four atoms that they have in the equation. N goes from +3 to what? +1. So that means it gains two electrons, right? So this one gains two electrons. So I need to make them equal. So there should be two P's and there should be one nitrogens. But again, the problem is that I can't really have two P's because the equation originally has four P's. So to make them equal, what I'm going to do is I'm going to double this. Multiply this by 4, multiply that by 2. If you multiply by 4 and 2, again the number of electrons are equal. So that means I should have 4 phosphoruses. So that's already 4. Make this 4 as well. So that's 4 phosphoruses, and there should be 2 nitrogen. So there's 1 over here, so make that 2. And there are 2 already on that side. So that is already balanced. So I've balanced this thing, I've balanced this thing, I've balanced H2PO2 minus 1 and N2O as well. How would I balance the OH and H2O? Like what should I write next to it? Like how many oxygens do I have? I have 8. I have 9 oxygens on this side. So 9 oxygens. There are 4 already over here. So there are 4 on that side. So this in total should come out to be, I mean, there should be 5 oxygens over here in total. I mean, there should be 5 oxygens. So how can I have 5 oxygens on this side?
One H2O, one OH minus.
Okay, so if I have 4 H2O and 1 OH, I mean the oxygen would be balanced. Like if I now I have 5 oxygens, right? But the hydrogens are not balanced. How many hydrogens do I have? That's 8 plus 1. That's 9. So how many hydrogens do I have over here? That's 8. So it shouldn't be 4 and 1 because the hydrogens don't get balanced that way. What other numbers can I use? And there should be 5 oxygens. I mean, can I use 3 and 2? Like if I use 3 and 2, the oxygens are again 5. I mean, there were 5 oxygens on this side. How many hydrogens do I have now? That's 3 and 4 over here. That's 7. And over here I have 8. Again, the hydrogens are not balanced. So think of another number. Let's switch 2 and 3. Now again, I have 5 oxygens. I needed 5 oxygens. I have 5 oxygens over here. How many hydrogens do I have? That's 6. And there are 2 hydrogens on this side, so that's a total of 8. So that's exactly 8 hydrogens on the right side as well. So now the hydrogens are also balanced. Is this clear?
Yeah.
Yes, sir.
So anyway, this is how you're going to balance redox reactions, and there's some equations which are known as disproportionation reactions. Disproportionation reactions are where uh, the same substance gets reduced and oxidizes at the same time. So that's a disproportion. So one example of a disproportionation reaction. So what happens here is that the same substance it gets oxidized and reduced at the same time. One example was there was one equation that you studied in AS which you had to remember, that was Cl2 reacting with NaOH and it would form NaCl and it would form NaClO3 and it would form water as well. Now, this is a disproportionation reaction because Cl originally is 0, N is plus 1, O is minus 2, H is plus 1, N is plus 1, Cl is minus 1, N is plus 1, O is minus 2. Cl over here, if you do the calculation, would come out to be plus 5. And H is plus 1 and O is minus 2. As anyway, so you figure out the oxidation states and then you try and figure out who's losing electrons and who's gaining electrons. So you would realize that it's Cl going from 0 to minus 1. So that means it gains 1 electron. But at the same time, it's the same Cl that's also going to plus 5. I mean, it would be a different Cl atom compared to the first one. But this time, it's losing 5 electrons. So how would I make the number of electrons gained and lost equal? So the first of the Cls must be multiplied by 5. There should be 5 Cl minus 1s. So there should be 5 Cl minus 1s compared to one of the Cls that is plus 5. So for every one of them losing 5 electrons, there should be 5 of them that would be gaining just 1 electron. And I've balanced this. This would be multiplied by 1. This would be multiplied by 5. So the total Cls at the start would be 6. So 5 of them, they gain 1 electron each, and one of them loses 5 electrons. And now the equation is balanced. You can balance the NAs, so that's 6 Na, so there should be 6 NaOH. And there are 6 hydrogens, so there should be 3 water molecules. So you've balanced the rest as well. So remember what a disproportionation reaction means. What does it mean, right? So is this clear to everyone? Ethan, Mohammed, is this clear? Minahil,
Yes.
Azra? ठीक है.
Yes, sir.
Okay. So this is all about redox reactions. Now what we're going to start is we're going to start just a brief introduction of what electrochemistry is. Now, what's the problem with these reactions? Why can't we make these reactions on our own? So far, whenever we studied redox reactions, the equation was already made for you. You just had to figure out who's the oxidizing agent, who's the reducing agent, what is getting oxidized, what is getting reduced, or at best you are asked to balance the equations. So if I don't have this equation, how would I know that what does phosphorus want to do? What does it like to do? Does it like to lose electrons or does it like to gain electrons? Like over here, there's an equation, and it clearly states that it likes to lose electrons, right? So if that equation is not in front of you, how would I know that what does each of the substance wants to do? Does it like to gain electrons? Does it like to lose electrons? Or would it like to do both? So now we're going to learn how to actually make these equations and predict redox reactions. Like who's going to lose electrons? I mean, the whole chapter is about this one. We need to figure out who loses electrons or likes to lose electrons. And we need to figure out who wants to gain electrons. Like here's a reaction. I've got Fe3 plus and I've got copper 1 plus, right? So the whole point of the chapter is how do I figure out what Fe3 plus and what copper 2 plus want, copper 1 plus want? Like I don't have an equation in front of me. So I have a solution that contains Fe3 plus ions. I have a solution that contains copper 1 plus ions. And I want to figure out or predict what would happen. Would copper 1 plus gain electrons? and Fe3 plus lose electrons, or would Fe3 plus gain electrons from copper 1 plus? And if it were to gain electrons, how many electrons would it gain? Like, would Fe3 plus gain 1 electron? Would it gain 2 electrons? Or would it gain 3 electrons? So, so a lot of things are unknown. So we're going to try and figure out how to solve this and how to develop a method where we could be very accurate about our predictions, where we could figure out exactly what's going to happen. So I'm going to start off with one example that you already know. So tell me a reactive metal that really likes to lose electrons. So for example, over here.
Potassium.
Okay, so let's start with potassium. So we're starting off. We're not sure about copper 1 plus or Fe3 plus, right? So we're starting off with a metal atom that we're sure of, that it really likes to lose electrons. So it's very reactive. It likes to lose electrons. It likes to form K plus 1 ions, and it gives those electrons away. So we're pretty sure what the behavior of potassium would be. That in any reaction, it would be the one that would be losing electrons. Now, I'm going to try develop a method to make this prediction more accurate and to have a value for that, so that we can quantitatively estimate. Right now we just know that potassium is more reactive. Uh, what I want is a specific value. I want to exactly know, like, how reactive is it? How much does it like to actually lose electrons? So we're going to build an electrode. So I'm going to take a solution, and this is what I'm trying to do. I'm going to take a solution, and the solution would contain K plus 1 ions in aqueous state. So it's going to contain K plus 1 ions in aqueous state. And I'm going to put a metallic rod that's made out of potassium. This is an oversimplification because the reaction would be too explosive. So it's not done exactly this way. But let's assume that I'm able to do that. So I'm going to place a potassium rod that's made out of potassium metal into a solution that contains potassium plus 1 ions. Now, what's going to happen? What's going to happen is the reaction that's mentioned above. The potassium is extremely reactive, so the potassium would immediately start to lose electrons and form potassium plus 1 ions, right? So immediately there's going to be a very vigorous explosive reaction, and all the potassium would start to lose electrons, and it would start to form ions, potassium ions. The same thing happens if you add sodium to water. Lots and lots of potassium ions are going to be formed, and it's going to be a very vigorous reaction. It's going to happen very, very quickly. Is this part clear?
Yeah.
Zaib, is this clear? Nabila, is this clear?
Yes, sir.
Yes.
Okay, so as soon as I put potassium in a solution that contains K plus 1 ions, nothing happens to the K plus 1 ions. This one that were already there. Instead, the potassium dissolves and starts to form more potassium ions. Now, when do you think this reaction would stop? Or, or would it go on forever? Would the potassium continue to react and continue to dissolve? Or would it stop at some
When
point?
that rod is completely dissolved.
Okay, so one point is that the rod completely dissolves, and it completely changes into potassium plus 1 ions, right? That's one point. That the potassium is so reactive that it would completely lose electrons, and it is going to turn into potassium plus 1 ions. But that's not what happens. What happens is, where are the electrons going? Potassium is constantly losing electrons. Now remember, this is a metallic rod. So the metallic rod has delocalized electrons. So all these electrons that potassium is losing are accumulated on this metallic rod. And as potassium continues to dissolve, there would be more and more electrons that would accumulate on the rod. So the rod would get a charge. There's going to be a buildup of negative charge on the rod. Is this clear?
Yes.
Is this clear to you? Minal, is this clear?
Yes.
Acha. So there's
Sir, can those electrons go into the water?
it's a metallic rod, right? A metallic rod is has delocalized electrons. So the metallic rod, metallic structure. Just a second, giant. Just 1 second. Let me show you the. Like, who's going to gain electrons in the water? At the moment, no one would be gaining electrons in the water. Uh, all the electrons, because it's a metallic rod, they would accumulate on the metallic rod, right? Is this point clear?
Understood.
I said now the point is the thing. I mean, this reaction cannot go on forever. Eventually, a point would come that the negative charge would become very, very large. The rod would become really negatively charged. And when it becomes really negatively charged, the negative electrons would start to attract. I mean, it's going to lose electrons up to a certain point. Sake, where we start here, Bikku. I said, so they're going to lose electrons up to a certain point. After a certain point, the rod would be so negatively charged that it would start pulling the K plus 1 ions back again. Because there's so many electrons, there's such a strong negative charge on the rod that has been built up that a reverse reaction would start and it would kick in. And that is when an equilibrium would be established. Like, the potassium would want to lose electrons and would want to form potassium plus 1 ions, but as soon as it forms potassium plus 1 ions, the negative charge over here would pull the potassium plus 1 back again, and the potassium plus 1 would gain those electrons back again. It would no longer be able to lose those electrons. So there's going to be a constant forward and backward reaction happening. And that is the point when equilibrium would be established. So is this point clear?
Yes.
Yes, sir.
So this is electrochemistry?
Yes. Okay. So the point is that the reaction would not go towards completion. The rod will not completely dissolve because of the buildup of negative charge, because the electrons are not going anywhere. The electrons are accumulating on the rod. So the potassium would only dissolve up to a certain extent, beyond which there would be so much negative charge that the potassium ions would get attracted back again. Now, what you're going to do over here is you're going to take a voltmeter and you're going to measure what voltage is built up on the and so you're going to measure the voltage that's built up on the rod. So if the voltage is highly negative, I mean, this is known as your E naught, or the voltage of the. I'm going to discuss E naught in a while. It's just the potential difference. So if the voltage is highly negative, that indicates that whatever the substance is, it really likes to lose electrons. So a very low potential, and we're not going to discuss negative or positive potential. We're going to discuss low potential, because potentials are relative terms. You always talk about potential difference, not. So a very low potential indicates that whatever the substance is, it really likes to lose electrons. So is this point clear?
Yes, sir.
Yes.
So So that is how you figure out. I mean, like you can put any metal over here, but you're going to get a value for this. In this case, if you open the data booklet, so if you open the data booklet, what you're going to realize is, I mean, there's a page where this information is provided. This one. So you can go and have a look at potassium, which is K. So K would be over here. This one. This is K. It's minus 2.92 volts. So that's, I mean, compared to the rest, that's highly negative. That's minus 2.92 volts. So it indicates that the substance really likes to lose electrons. As a compared to this, if I had magnesium over here, would the potential be more negative or less negative?
Less.
Because magnesium doesn't really like to lose that many electrons. So the number of electrons that would accumulate on a rod that's made out of magnesium. So magnesium would be this. I'm just going to copy this and change this to let's change this to magnesium. So magnesium is kind of less reactive. So let me change this. This is magnesium now. And again, I'm going to add it to magnesium aqueous ions solution. And now the issue would be that magnesium is still reactive, but not that reactive. So it's going to produce these Mg2 plus ions, but not a lot of them because it's not very reactive. And the number of electrons that would be accumulating on the rod, they're not going to be that many. So compared to the first one, so now compared to the first one, the electrode would not be that negative. It's not going to. There's not going to be a very large negative charge built up on the rod. Mg would try to, and eventually in equilibrium would be setting in very quickly. Magnesium would be trying to lose electrons, but the negative charge would be pulling the magnesium ions back again. So there's going to be a reversible reaction, and you have a potential for magnesium as well over here, right over here. You've got magnesium that's minus 2.38 volts. So this one is minus 2 point. This one is minus 2.38 volts. So the point is that these are known as electrodes. These are known as standard electrodes. We're going to talk about. I'm just giving you the concept right now. So the main point is that now you have a quantitative value, and you can now compare. I mean, previously we knew that potassium was more reactive than magnesium. Now we exactly know how much reactive. Now we have a very specific value which we can compare, and we can get an idea of how much reactive is potassium compared to magnesium. So is this clear?
Yes, sir.
Yes, sir.
So that's your standard electrode. So the definition of a standard electrode, again, I haven't really, I'm just writing the definition. I haven't really gone into a lot of detail about this. And this is not the proper way to actually make an electrode at the moment. This is just to give you the concept. So standard electrode is an electrode not standard electrode potential. So it's the potential difference calculated between a standard electrode between a standard electrode and a standard? I said we're going to talk about the standard hydrogen electron much later on. Right now, just remember this E naught is your potential difference. It's the potential difference that's calculated on an electrode compared to something. I mean, it's always potential difference. You always compare it with something. So we're going to talk about this something later on. Remember, potential difference is always between 2 points. So, so we're going to discuss that later on. So is this clear?
Yep.
Yes, sir.
So just remember, I mean, the first point, a very low potential indicates that the substance really likes to lose electrons. So that's how we're going to predict redox reactions. Like if the potential is really low, we know that it wants to lose electrons. So that's one. I mean, there are two things. One is a very low potential indicates that the substance likes to lose electrons, and the opposite is also true. A very high potential indicates that the substance likes to gain electrons. We didn't do examples for that, so we'll do that in the next class, in the coming class. Okay. So
Perfect.
there's going to be class tomorrow, right? Remember that. Okay, everyone. Take care. Allah
Allah
Hafiz.
Hafiz, sir.
Thank
Allah
you.
Hafiz.
Thank you.
Okay, Allah Hafiz.